Yeah, I want to talk about cluster data. So we have repeated measurements from the same individual. So we have dependencies between these observations, and at the same time we have the high dimensional case where we have many covariates and have to deal with it too. So we talk about mixed models and we talk about regularization. In the mixed model setting, we have this joint likelihood where we have this response y. No. Yeah. And this the random effects u, and then we have the qu for the random effects. This is the covariance matrix, and yeah, this integral is typically cannot be calculated analytically, so we use here the Laplace approximation of it. And yeah, this looks like this. So we have this separate form with the fixed effects on the left-hand side, and then these quadratic form of the random effects on the right-hand side. And yeah, this is the approximation we use here. And we can build some score functions here. Then we have the score functions for the fixed effects and for the random effects as well here. We need that for the optimization in the fitting routine. With some things here, the derivative of the link function here is in the D matrix, and then we have the variances in the sigma matrix. And we also need the Fisher matrix here, and we have here the upper left part for the fixed effects, and then the other parts for the random effects and some mixed parts as well. On the other hand, we want to estimate the covariance matrix of the random effects, and for this we have this nice formula here. And then we can the classical way is we have some initialization values, and then we first estimate or iterate over this delta vector, which is the fixed and the random effects combined. And then we have to compute these theta for the covariance matrix, and then we repeat that until convergence. As I said, we want to use the LASSO penalty as well, or we want to use regularization. At the moment, we use the LASSO penalty, but we don't use the classical LASSO. Instead, we use an approximation which is differentiable. So we have this square root of the beta squared plus c, and c is a very small but positive number. So we have this approximation is differentiable at 0. For our case, we use c is 10 to the minus 5, so a very small number. And then we are able to calculate the derivative or the score function here and the second derivative for the Fisher matrix as well, which can be good for the optimization steps. What we lose here when we use this approximation is in the LASSO case, some parameters or some covariates, or the effects of the covariates can be estimated to exactly 0. That is, we lose this property here, but we gain it in some way back if we define a small threshold. In our case, 10 to the minus 3, and every estimation which is below this threshold is manually set to 0. So we have this estimation to 0 back in that way. And in the where we use the LASSO case, then we standardize all the covariates in first. So we have the penalization effect is equal on all covariates. So when we have here this threshold of 10 to the minus 3, then we have 0.1% of the standard deviation cut off in if we manually set the estimation to 0 here. So it's not a big change in the accuracy here. What we have done is we take two R packages. We first take this BLME package, which is normally used for Bayesian models. And we have posterior is likelihood times prior. And then we took it to the log scale. So we have log likelihood plus log prior. And then we can replace the log prior with our LASSO penalty. And we can use these packages. It turns out that BLME has big problems with settings where P is equal to N or bigger than or larger than N. So we have researched a new package, this GLM-TMB package, where every situation works. So we can handle P larger N scenarios as well. Then we had the simulation study where we have this some design matrix X, then some true parameters where we have P1 signal variables and P2 noise variables. So because of our LASSO setting, we want to identify these noise variables at the end because unregularized models are not, our models should be better in identifying these noise variables than the unregularized models. That's the idea here. And if we have random slopes, we have settings with random slopes and settings without random slopes. And when we have slopes here, then we choose the covariates at random. So it can be signal variables, it can be noise variables as well. Then we get our random effects also from a normal distribution. And get the Z matrix for the random effects. And then we have our model with the fixed effects and random effects and some random noise at the end. And then we also we always go to lambda sequence to find the best lambda, and we go from the maximum value, which shrinks all the covariates to 0, from this value to 0, where this is the unpenalized case. Then we choose the lambda which leads to the best AIC. Compute the RMSE between the estimated and the real beta. We split this comparison into noise and signal. And then we compare the results of this or both packages, and we can also compare it with the LME4 package, which is the unpenalized case. Which, as I said, we have these three methods. We have always 100 observations. We have always 5 signal variables, and we vary between 25, 95, and 295 noise variables. So we have n larger p, n is equal to p, and p larger n. Then we have some correlation in the data. So we have 0, 0.3, and 0.7, which means we have a covariance matrix where the diagonal is 1 and all other components have one of these values. So if we have one setting with complete no dependencies, and then we have one setting with all the correlations are 0.3 and another setting with all the correlations are 0.7. We have one or two grouping variables, and we have always 15 groups, and we have always a random intercept, and we have settings with 0 slope and settings with 2 slopes. We have some limitations. As I said, LME4 is unpenalized and only works for n larger p, and BLME as well. So the method comparison will be only with 25 noise covariates, and all the other comparisons are only with the GLMM TMB package. When we compare the methods, we see that our packages work better than LME4 for the noise variables, which could be expected because of the penalization. And for the signals, it's a little bit overlapping. Then we have the number of covariates. I don't really trust these results of 300. I have to check it. This is maybe it has to be higher there. And for signal, it's again overlapping. Then we have the number of grouping variables, where the results are not that different from each other. And then we have the strength of correlation. Difficult. And we see that if the correlation is higher than the RMSE growth or the variance or the variability of the RMSE growth. Currently working on real data application as well. We have a data set with 111 observations and 4,088 covariates, which is grouped into 28 groups or clusters with 2 to 6 observations. There's some papers on this data set, and they used some different variables for random slopes, which I would take into account as well. It's this, and we want to maybe get another data set, and we could extend the simulation study also to the other families. And what we also want to do maybe is add some more kinds of types of penalties. At the moment, we are only using this LASSO approximation, but maybe that we can extend this as well. The one thing, the main one advantage of getting these packages or go into these packages and adapt them is that we we don't have to implement the syntax by ourselves, so we get the syntax from these packages. So that was also good. I think that's it.